Welcome everyone. Just a quick note, these lectures move at a faster pace than in-person classes. They're meant to be paused, reviewed, and rewatched multiple times. Things should start making more sense as you pause and go over the material. If you haven't already, try increasing the speed to save time. So what are statistics? Statistics is a study of collecting, analyzing, interpreting, presenting, and organizing data. What is data? Data is collected information. It doesn't have to be numerical, as we'll see shortly, but it usually is numerical and represented as a list of numbers or array of numbers where each number refers to a specific measurement or count, usually in some specific unit. For example, a company tests the sodium content in 100 snack bars. This data set of 100 data points is a list of 100 numbers. I call each number a data point. Each number represents the sodium content of a different snack bar in units of, say, milligrams per snack bar. If you convert to a different unit, like grams per snack bar or milligrams per ounce, you'd have to change the values of the data accordingly to convey the same information. What are different types of data? Data is categorized into 4 different scales called levels of measurement. The lowest level is nominal scale. That's qualitative data that has no inherent numerical value or ordering. Examples of nominal data are data sets consisting of everyone's sex, eye color, blood type, or phone number. There's no meaningful way to say green eyes is higher or lower than blue eyes. The same with phone numbers. They're numerical, but in appearance only. They don't have any actual numerical value, where it will make sense to say this phone number is higher or lower than that one. The next level is ordinal scale. That's data that has ordering, but is not on a scale with equal intervals. So like nominal scale, it's also not inherently numerical data, but the order of the values matters. Examples of ordinal scale are data from surveys where participants were asked to give ratings like poor, fair, good, and excellent, or data consisting of education levels or military ranks. For ordinal data, assigning numerical values to data like to label poor, fair, good, and excellent as 1, 2, 3, and 4 is meaningful, but only in the sense that 1 is the lowest, then 2, then 3, not in the sense of the real values of each number where the interval or difference between 1 and 3 is equal to the difference between 2 and 4. The intervals between the values poor and fair, or between fair and good, are vague. They're not uniform or measurable, and they're certainly not equal intervals. So the only numerical value that is meaningful in ordinal data is in terms of their order. The next 2 levels are quantitative and have real numerical value. First, we have interval scale. Those are numerical values on a scale with equal intervals, but don't have a true 0 point. That is a 0 that actually means none of what you're measuring. And therefore, ratios are meaningless. Examples of interval scale data include things like IQ scores and temperature measured in degrees Fahrenheit or Celsius. The temperatures we call 0 degrees in Fahrenheit or Celsius were arbitrarily chosen. 0 degrees does not mean 0 heat. In Celsius, for example, 0 is the freezing point of water. But freezing water is just a random physical process of a random chemical. It's not some universal meaningful 0 point for temperature. So because 0 degrees is not the actual temperature where there's actually 0 heat, ratios don't make sense. For example, you can't say that 50 degrees Celsius is twice as hot as 25 degrees Celsius, or that 100 degrees Fahrenheit is double 50 degrees Fahrenheit. The numbers don't work that way in this scale. The same logic applies to IQ scores. Someone with an IQ of 150 is not 50% more intelligent than someone with an IQ of 100. IQ is measured on an interval scale, so we can compare differences but not ratios. Here's another way to see why ratios don't make sense with interval data. Let's say you have 2 temperatures, 100 degrees Fahrenheit and 50 degrees Fahrenheit. 100 is double 50, right? Now convert to Celsius. 100 degrees Fahrenheit is about 38 degrees Celsius, and 50 degrees Fahrenheit is about 10 degrees Celsius. So you clearly see 38 is not double 10. The ratio completely changes once you switch units. That's because there's no true 0 anchoring the scale. So ratios or multiples aren't consistent or meaningful across the scale. Finally, we get to the highest level of measurement, the ratio scale. That is where the 0 point really means zero, the complete absence of the thing you're measuring. And here ratios or multiples are meaningful. You can't say that someone who weighs 100 kilograms is twice as heavy as someone who weighs 50 kilograms. Ratio scale data includes most physical and financial measurements, things like height, weight, age, income, sodium content, and so on. We'll come back to these 4 levels of measurement after we've explored some key concepts in descriptive statistics. Another important distinction is between discrete versus continuous data. Discrete data consists of specific separate values with no intermediate value, like data that has only whole numbers. For example, data consisting of everyone's age or of the number of something or another, like the number of late days for every student. Also, all nominal and ordinal data are discrete. In contrast, continuous data can take on any value within a certain range. These typically involve measurements, like weight. You can weigh 98.886 pounds or 98.887 pounds and so on. The same with height, speed, or time spent in the office. Another important distinction between types of sets of data is population versus sample. Population data is data about the entire population, like a census, or more generally any data where we're only interested in the data set itself and we're not using it to make inferences about a larger population. For example, data about the scores of the students in a class, we're not interested in using the data to make guesses about any other students from other classes. I'm only interested in these student scores. In contrast, when we collect data for a science experiment or survey, what we're really interested in is a large population of the country or the world that's not in the data set. And we're using our data set as a sample to infer about the population. The same as when a company tests a sample of products for quality control. If the company manufactures 1 million phones, it will pick, say, 300 phones to test to make sure they're good. What the company really cares about is not those 300 phones, but the entire population of 1 million phones. The total number of data points in the dataset for population is called the population size and is noted by an uppercase N. And for sample data, the total number of data points is called the sample size and is denoted by a lowercase n. Statistics is divided into 2 categories: descriptive statistics, which we'll cover now, and inferential statistics or statistical inference, which we'll get to later in the course. Inferential statistics is specifically about sample data, how to use sample data to make inferences about a larger population. But as I said, we'll start with descriptive statistics, which is about how to make sense of the data set itself. An important part of descriptive statistics involves using measures to quantify and highlight essential characteristics of the data. They are divided into 3 categories of measures: measures of location, measures of dispersion, and measures of shape. Any one of these measures is called a parameter for population data and a statistic for sample data. We'll start with measures of location. Those are measures that give you an overall sense of the center and distribution of the values of the dataset. You can think of location in this context as where on the number line the data values are located. Measures of location include min, max, mean, median, mode, and quantiles, which include quartiles and percentiles. We'll now go through each one of these. Min and max are just the highest and lowest values of the data set. Mean is the average. Just like you saw with the size of the data set, that there are 2 different symbols for size. For population, the size is denoted by an uppercase n, and for sample, the size is denoted by lowercase n. There are also 2 different symbols for mean, depending on whether we're dealing with a population or a sample. For population, the mean is this Greek letter mu, and for sample, it's x bar. How do you calculate the mean? It's the sum of the data divided by the size, or the total number of data points. For example, take the dataset 2300. This dataset could be about anything. Let's say it's about how many apples each person out of a group of 4 people got. What is the average? The sum is 2 plus 3 plus 0 plus 0 equals 5. The size of the dataset, uppercase or lowercase n, is 4. Right? There are 4 values. So the mean is 5/4 equals 1 1/4, 1.25. Median is the middle value in the data set, where the numbers are arranged in ascending order. If the data set has an even number of observations, the median is the mean of the two middle numbers. For example, in the same data set, 2, 3, 0, 0, when you order it, you get 0, 0, 2, 3. So the two middle values are 0, 2. You take their mean. The mean of 0 and 2 is 1, so the median is 1. Let's say you add another value to the data. Let's say 2. Now, you have an odd number of data points. So you order it, you get 0, 0, 2, 2, 3. There's only one value in the middle, so you don't have to do any averaging. The median is just that value, 2. The mode is the value that appears most frequently in the data set. In this same example, 0 appears twice more than any other value, so the mode is 0. The data set could have one mode, it could have two modes, or it could not have any modes if they all appear equally. If it has two modes, it's called bimodal, and if it has, in general, more than one mode, it's called multimodal. To find the median, we divided the data into two halves, and the middle value is the median. The idea of quartiles is to repeat the same process again to further take the median of each half of data to get two new values. Now the data is divided into 4 parts by 3 cuts. The median, which when you first divided, you got the median, and then the 2 new cuts. That's total 3 cuts. That divides the data into 4 parts. Each of these 3 cuts is called a quartile. The first quartile, Q1, is a value for which 25% of the data fall below this value, and 75% of data fall above it. The second quartile, Q2, just means the median, which divides the data right in half. And the third quartile, Q3, is a value for which 75% of the data fall below it and 25% fall above it. For example, take this data set shown here. If you order it, you get the median is the average of 8 and 10, which is 9. Now, you divide this half of the data. So the median of this half is 4, so that's Q1. And for Q3, you take the median of this upper half, so you get 15. The median is not included when calculating Q1 and Q3. If the size of the dataset is even, like we saw in the previous slide, it's obvious that you simply divide the dataset into 2 halves, right? So you just take this half and this half, because the median is 9 and it's not even in the dataset. But even if the dataset is odd, the middle value, which is the median, is not counted as either the top half or the bottom half of the data. So you never count the median in the data, whether it's even or odd. Pause this video and look at the example to be clear about what I just said. One widely used method for displaying the spread of data is the box plot, or box and whisker plot. It's a graph that shows the min and max and 3 quartiles like this. The median is here. This is Q1. This is Q3. And the whiskers go out to the min and the max. So each 25% of data is in another section. A box plot can be horizontal, like the one here, or it can be vertical. So I have a question. Clearly in this box plot, this 25% and this 25% are smaller than this 25% and this 25%. How could that be? Shouldn't each 25% be equal? The answer is yes, of course they're equal, but in terms of the data itself, not in terms of the number line. Let's say there are 4,000 data points in the data set that's represented by this box plot. That would mean that 1,000 data points go from like 10 to 23, and another 1,000 are between like 23 and like 34, and another 1,000 go from like 34 to 56, and so on. So the numbers are more concentrated in the lower numbers and more spread out in the higher numbers. A backsplash is a one-dimensional graph. There's no y-axis. The height of the backsplash doesn't mean anything. It's just a visualization. Percentiles is the same idea as quartiles, but instead of making 3 cuts in the data for 3 quartiles, you make 99 cuts, dividing the data into 100 parts. Each part contains 1% of the data. N% of the data falls below the nth percentile. So for example, if the 86th cut falls in the value 70, or falls between two values and their average is 70, that means that 86% of the data points are less than 70. So if the data set is about student scores on an exam, and each data point represents a student, that means that 86% of the students got below 70. We're not going to calculate percentiles for data sets for this course, but you have to understand what they mean. We've finally gone through the measures of location. Let's go on to measures of dispersion. Measures of dispersion describe how spread out or varied data points are. Two data sets can have the same mean, but the data points could be much more spread out in one than in the other. Why is it important how spread out the data points are? Because more spread out means less consistent. If you're using data as a prediction for the values you may get in the future, more spread out means greater risk and a less reliable estimate. The measures of dispersion that we'll cover are variance, standard deviation, coefficient of variation, CV, range, and interquartile range, or IQR. The most important measure of dispersion is how far on average the data points are from the mean. How can you calculate the average of how much the data points differ from the mean? It would seem that calculating this is straightforward. You simply calculate each deviation from the mean, meaning you subtract the mean from each data point, and then take the average of all these deviations. But this doesn't work. The sum, and therefore also the average of the deviations from the mean, will always be 0 for any data set. Why is that? Because the mean is a balancing point of the data. When you subtract the mean from each data point, the positive and negative deviations cancel each other out exactly. Let's see if it works in the data set we're using above, 2300. We found that the mean was 1.25. So to calculate each deviation from the mean, we have to subtract 1.25 from each data point. So we take 2 minus 1.25 is 0.75, 3 minus 1.25 is 1.75, 0 minus 1.25 is minus 1.25, and again minus 1.25. Sure enough, the sum of these is 0. And that's what I can get for any data set. It will always be 0. So what measure could you use for an average deviation from the mean? We could square each deviation. That will turn any negative into a positive. Now in our example, the sum of the squared deviations, so 0.75 squared, 1.75 squared, negative 1.5 squared, negative 1.5 squared, you sum it all up, is 6.75. So what is the mean or the average of the squared deviations? Mean is a sum divided by n, right? What is n? The total number of data points is 4. So the mean squared deviation is 6.75 over 4, which is 1.6875. So this is the population variance, and it is denoted by this Greek letter lowercase sigma squared. For a sample, again we use a different symbol, s squared instead of sigma squared. But for variance, not only is the symbol different, but the formula is also different. Now you can understand why we need different symbols for population of a sample, because in like this case it's entirely different formula. If the data set is a sample, we have to divide by n minus 1 instead of by n. This is called Bessel's correction. So for a sample, if n is 4, we have to divide by 3, and we get the sample variance is 6.75 over 3, and it's equal to 2.25. Why is this correction needed? The exact reason is beyond the scope of this course, but I can try to give a little intuition. The sample mean, which we are using to calculate the deviations of the mean, is itself calculated from the sample. This makes the deviations from the mean slightly smaller than they would be for the true population mean. So when we divide by n minus 1, that slightly increases the variance to correct for this underestimation. So here are the general formulas for population and sample variance. Just follow these 4 steps. And go over the example in the previous slide to make sure you understand how to do it for every example. First, subtract the mean from each data point, whether you're using population mean mu or sample mean x bar. xi just means each data point, from x1, which is the first data point, to x uppercase lowercase n, which is the last data point. I is an index that goes from 1 to n. Second, square each result to get the square deviation. Third, sum up all of the square deviations. This symbol is an uppercase sigma, and it means summation. And this notation just means to sum up the values of the formula to the right for every value of the index I from 1 to n. Fourth, divide by the population size, uppercase n, if you're using population mean mu, or divide by the sample mean lowercase n minus 1 if you're using the sample mean x bar. So the obvious problem with variance is that it's the square deviation instead of the actual deviation. Another problem with variance is that the units of the variance are the square of the units of the data. If there's in dollars, the variance is in square dollars, which is not even intuitive. And it's not the same units as the data. We want to have units that are the same as the data. So, although the variance is a useful measure for spread, the more common measure is standard deviation, which is just the square root of the variance and has the same units as the data. It's noted as sigma for population and S for a sample. And here are the formulas in full for the population and the sample standard deviation. They're just the formulas of variance, but inside of a square root. You might be wondering, why not use the absolute value instead of squaring and then unsquaring? The answer is, that's also a valid measure for spread. It's called the mean absolute deviation. But the advantage of the standard deviation is that it's more sensitive to larger deviations and has better mathematical properties for analysis. Standard deviation tells you how spread out the data is in an absolute sense. This is not very useful when comparing data sets that have very different means. Compare, for example, someone with an average income of $20 million with a standard deviation of $1,000 versus someone with an average income of $500 and a standard deviation of $100. Whose income is more stable? In absolute terms, 100 is less than 1,000. But relative to the average income, 1,000 out of 20 million is 0.005%. And 100 out of 500 is 20%. So in the relative sense, this one is much less stable because it's a much bigger variation. So it's technically true that in absolute terms, the person with $20 million income has a less stable income because it tends to fluctuate by a much larger amount of money. But what really counts is the relative stability. And in this sense, the one with the 20 million has a much more stable income, with only 0.005% fluctuation. This relative standard deviation is called coefficient of variation, or CV. And The formula for it is the standard deviation over the mean. It's typically expressed in terms of percent. That's why I write times 100% in the formula to indicate that the result should be multiplied by 100 to convert it into percentage. Notice that the units of dollars disappeared because they got cancelled out by appearing in both the numerator and the denominator. CV is therefore always a unitless quantity. So that means that if you convert the mean and standard deviation from dollars to euros, the CV will not change because it doesn't depend on the units. Also, you can compare CVs of different data that are expressed in different units. If you have one data set in dollars and another data set in euros, it still makes sense to compare their CVs because CV doesn't depend on units. We're up to the two final measures of dispersion, range and interquartile range. The range is the max minus the min. It's a single value, not a spread. In our little data set that we've been using, 0023, you can say in everyday language, and even in a statistics class in some other context, that the range of values is between 0 and 3. But that's not what is meant by range as a measure. The measure of dispersion called range is 3 minus 0, which equals 3. The range does not tell you what the min and max are, only what the difference is. In general, when you hear the term range used in a discussion about statistics, you have to determine from the context whether it is meant as a measure or in the everyday sense, like when you say the range is between 0 and 3. The interquartile range, or IQR, is Q3 minus Q1, which is the range of the middle 50% of the data. In this example we've been using previously for quartiles, the range is 19 minus 1 equals 18. And the IQR is 15 minus 4, which is 11. Why are min, max, Q1, and Q3 measures of location, but range and IQR are measures of dispersion? Because for range and IQR, only the spread matters, not the location on the number line. A dataset with a min of 0 and a max of 3 has the same range as a dataset with a min of 1,000,000 and a max of 1,000,003. And the same goes for IQR.